stars like our sun live for billions of years, fusing hydrogen into helium and shining steadily. But no star lives forever. When the fuel runs out, something new emerges. For a star like the sun, death is not a dramatic supernova. It is a quiet, gradual transformation into a tiny, dense object called a white dwarf. This is the future of our sun, and the fate of most stars in the galaxy. White dwarfs are fascinating. They are Earth-sized, but contain the mass of a star. Their gravity is immense. They are supported not by nuclear fusion, but by the strange laws of quantum mechanics. And they hold the key to understanding how stars die, how planets survive, and even how we measure the age of the universe. Today, we're going to explore white dwarfs, what they are, how they form, and why they matter. From main sequence to red giant. To understand white dwarfs, we need to look at the life of a sun-like star. For about 10 billion years, our sun has been fusing hydrogen into helium in its core. This is the main sequence phase. But eventually, the hydrogen in the core runs out. The core contracts and heats up, while the outer layers expand and cool. The sun becomes a red giant, a bloated star hundreds of times larger than it is today. During the red giant phase, the sun will swallow Mercury, Venus, and possibly Earth. Its outer layers will drift away into space, creating a beautiful planetary nebula. But the core, now made mostly of helium and carbon, will continue to contract. It is this core that becomes the white dwarf. The red giant phase lasts only a few 100 million years, a short final chapter in the star's long life. Shedding the envelope. When the core of a red giant contracts enough, it becomes hot enough to fuse helium into carbon and oxygen. This provides a temporary energy source. But helium fusion is unstable, leading to thermal pulses that blow off the star's outer layers. These layers form a glowing shell of gas, a planetary nebula. The name is misleading. These nebulae have nothing to do with planets. Early astronomers thought they looked like planetary disks through small telescopes. The planetary nebula expands and fades over tens of thousands of years. What remains is the star's core, a hot, dense ball of carbon and oxygen, about the size of Earth, but with a mass comparable to the sun. This is the white dwarf. Initially, it is extremely hot, up to 100,000 Kelvin, but it has no fusion to sustain that heat. It will slowly cool for the rest of its existence. Tiny but massive. A white dwarf is an extreme object. Its radius is about the same as Earth's, roughly 6,000 to 8,000 kilometers. But its mass is typically 0.5 to 1.4 times the mass of the sun. This means its density is enormous. A teaspoon of white dwarf material would weigh about a ton. The gravity on its surface is about 100,000 times stronger than Earth's. White dwarfs are not made of ordinary matter. The atoms are crushed together so tightly that electrons are stripped away and form a degenerate electron gas. This electron degeneracy pressure is what supports the white dwarf against gravity. Unlike normal gas pressure, degeneracy pressure does not depend on temperature. So a white dwarf can be cold and still resist collapse up to a limit. The maximum mass. There is a maximum mass for a white dwarf. This was discovered by the Indian physicist Subrahmanyan Chandrasekhar in the 1930s. He calculated that if a white dwarf's mass exceeds about 1.4 times the mass of the sun, electron degeneracy pressure can no longer support it. The star will collapse further, triggering a supernova explosion. This limit is called the Chandrasekhar limit. Stars more massive than about 8 solar masses do not become white dwarfs. They become neutron stars or black holes. But for stars below that threshold, the white dwarf is the final state. The sun's mass is 1 solar mass, so its white dwarf will be well below the limit, about 0.6 solar masses. The Chandrasekhar limit is crucial for understanding Type 1a supernovae, which occur when a white dwarf in a binary system accretes enough mass to cross the limit. A slow fade. After the formation, a white dwarf is extremely hot, but with no fusion, it simply radiates its stored heat into space. Over time, it cools and dims. The cooling process is very slow because the white dwarf is small and has a high heat capacity. It takes billions of years for a white dwarf to cool to the point where it becomes invisible. The oldest white dwarfs in our galaxy are about 10 to 12 billion years old. Their temperatures are around 3,000 to 4,000 Kelvin, still hot enough to glow faintly red. Eventually, they will become black dwarfs, cold, dark objects that emit no light. However, the universe is not old enough for any black dwarfs to exist yet. The cooling timescale is longer than the current age of the universe. Planets around white dwarfs. What happens to planets when a star becomes a white dwarf? During the red giant phase, inner planets are engulfed and destroyed. But outer planets like Jupiter and Saturn can survive. They will continue orbiting the white dwarf, though their orbits may shift due to mass loss. Even more intriguing, some white dwarfs show evidence of rocky debris in their atmospheres, the remains of asteroids or planets that were shredded by the white dwarf's gravity. In recent years, astronomers have directly detected planetesimals and even intact planets around white dwarfs. The James Webb Space Telescope has studied the atmospheres of white dwarfs, finding elements like calcium, magnesium, and iron, evidence of rocky material falling in. These observations tell us that planetary systems can survive stellar death, and that white dwarfs can host debris disks and possibly even habitable planets in their distant, cold orbits. White dwarfs as cosmic clocks. White dwarfs are useful tools for astronomy. Because their cooling rate is predictable, we can estimate the age of a white dwarf by measuring its temperature and luminosity. This allows us to date stellar populations, for example, the age of the galactic disk or the age of globular clusters. White dwarf cosmochronology has confirmed that the oldest stars in our galaxy are about 12 to 13 billion years old. White dwarfs are also important for understanding dark matter. Some theories suggest that dark matter could accumulate inside white dwarfs, altering their cooling rates. By comparing observed white dwarf cooling with models, we can place constraints on dark matter properties. White dwarfs are also used as standard candles for certain distance measurements, though not as precise as supernovae. The Sun's quiet legacy. In about 5 billion years, the Sun will become a red giant, engulfing the inner planets. Then it will shed its outer layers, creating a beautiful planetary nebula. What remains will be a white dwarf, a tiny, dense sphere of carbon and oxygen, slowly cooling for eternity. Our Sun's white dwarf will be about the size of Earth, shining faintly for billions of years before fading to black. White dwarfs are not dramatic like supernovae or black holes, but they are the most common endpoint for stars. They tell us about the past and future of our own star, about the survival of planetary systems, and about the age of the cosmos. They are quiet witnesses to the cycle of stellar life and death, and a reminder that even the Sun will one day become a cold, dark relic. What do you think? Would you want to visit a white dwarf, or is the future of our Sun too far away to imagine? Let me know in the comments. Thanks for watching Daily Dose of Space. Stay curious, and I'll see you tomorrow.